Here we're going to be discussing the local well-posedness of the nonlinear Schrodinger equation in HS when S is larger than half the dimension. So first things first, what is the nonlinear Schrodinger equation? Well, this is the equation I dt plus Laplacian of u equals u mod u to the p minus 1 with initial data at time 0 given by u0, which is a function in HS of Rn. So what's this parameter p? Well, for us today, p is going to be an odd integer, but more generally we could take anything larger than 1. And as I said, we're going to be looking at s larger than n over 2. We want to show the local well-posedness of this equation, so there's 4 elements to consider. The first is local existence of solutions. Obviously, you're not going to get very far without that. The second is the continuous dependence of the solution on the data. If you move your data a tiny bit, your solution should only change a little bit. The third is the question of uniqueness of solutions. And the fourth, the cherry on the top, is the question of persistence of regularity. So this means that if your initial data has more regularity than just lying in HS, say it lies in HS primed, where S primed is larger than S, then your solution should preserve that regularity and also lie in HS primed. So before we go any further, I just want to introduce the notation that I'll be using. So here it is. We have the usual HS norm when S is any positive integer, real number, sorry. We'll be working in this space of continuous functions on an interval I into HS as defined above, which I'm often going to denote as C0t HSX when the interval is minus t. Lastly, St of f is the free evolution operator for the Schrodinger equation. So this is the solution to the system to the linear Schrodinger equation with initial data given by f. So I'm not going to go into any more detail on this. I think it's all fairly standard. If you're not sure about something, you can pause the video and look in more detail. So now I'm going to carry on with our problem. So today we're going to focus just on the local existence and the continuity aspects of local well-posedness. And for both of these, we need to specify the space we're going to be working in. So since we're looking at well-posedness in HS, we're going to be working in the space of continuous functions on some interval into HS. So as I just said, I'll often be denoting this as C0t HSX. And since solutions in this space obviously don't necessarily have enough differentiability to be classical solutions of the equation, when I talk about a solution, I really mean a strong solution. So this is a u, so that u equals s of t u0, so free evolution of the data, minus I times the integral from 0 to t of s of t minus tau u mod u to the p minus 1 of tau d tau. And this is the classical Duhamel formulation of a solution to the nonlinear Schrodinger equation. We'll construct a solution in this space by a contraction mapping argument. So that's to say that we'll show that the solution map, this phi of u, is a contraction map on some ball BAT, which is a set of functions in C0t HSX with norm in this space less than or equal to A. And we'll have to choose A sufficiently large and T sufficiently small so that phi is a contraction map on this space. So if phi is a contraction map, then it will have a fixed point in this ball, and by definition the fixed point is a solution to the nonlinear Schrodinger equation on the interval minus t, so just locally. So to show that phi is a contraction map, we have to show two things. We have to show that phi maps this ball to itself. So whenever u has norm less than or equal to A, phi of u should as well. And we also have to show that it's a contraction. So whenever u and v lie in this ball, the norm of phi of u minus phi of v in C0t hsx should be less than or equal to half the norm of u minus v. Obviously, we don't necessarily need a half there, it could be anything less than 1, but just for concreteness, I'm taking a half. So the main tool we'll have for proving these estimates is a Leibniz type inequality in Sobolev spaces. So this is the inequality u times v in hs is less than or equal to some constant which depends on the dimension and on s times the norm of u in L infinity, the norm of v in hs, plus the other way around, so u in hs and v in L infinity. And to see why this is called a Leibniz type inequality, at least by me, you can take s equals 1 and see that it gives you what you expect from Leibniz rule. Clearly this would hold for more than just 2 functions. We can generalize it to having n functions. So then we'll have the product u1 up to un in hs is bounded by, again, some constant, which is now also going to depend on capital N, times the sum over j equals 1 to n of the norm of uj in hs multiplied by the norms of all the other u's in L infinity. So each time one of the ui's goes into hs, all the others go into L infinity, and you can easily check this follows from the above inequality. Now, I'm not going to prove these now, but I'll just comment that to prove them you use a Littlewood-Paley decomposition of the functions u and v in Fourier space. But as I said, I'll leave that for now and get on with the proof of existence. So it's to make good use of this inequality that we choose p to be an odd integer, because in this special case, we can write the nonlinearity as u mod u to the p minus 1 equals u times u bar, so the complex conjugate, to the q. So here q is half p minus 1. So now this is just a polynomial, it's just u to the q plus 1 times u bar to the q. So then we can bound the nonlinearity in hs using the previous inequality by some constant depending on n, s, and p, because that governs how many terms there are in the polynomial above, multiplied by the norm of u in hs and the norm of u in L infinity to the power of p minus 1. So with this inequality in hand, we're now ready to show that phi is a contraction map on BAT for some choice of A and T. So we need to first show that phi maps the ball to itself. It's a self-map, i.e. whenever the norm of u is less than or equal to A, we need the norm of phi of u to also be less than or equal to A. So we need to bound phi of u in terms of the norm of u. So first we have this very simple inequality from triangle inequality. We just split phi of u into the free evolution term and the nonlinear Duhamel term. And the first term, the linear term, is very easy to bound using that s of t is an isometry on hs. So the norm of s of t of u0 in c0t hsx is the supremum over the interval minus t of the norm of s of t u0 in hs, just by definition. And now, since s of t, as I say, is an isometry on hs, which you can easily check just, for instance, by taking the Fourier transform and using the definition of the Sobolev space, this s of t has no effect. It doesn't change the norm at all. So when we take the supremum over all times, this quantity is independent of time, so we just have the norm of u0. Now we have to bound the second term, which is slightly more complicated, but still not too complicated because of the nice inequality we proved above for the nonlinearity in hs. So this time we want to bound the integral in c0t hsx. So this is looking again at the supremum over the interval of the norm of the integral in hs. And now we use Minkowski's inequality to move this HS norm inside the integral in time. So we can get rid of it on the outside and move it on the inside. And this is basically an integral version of the triangle inequality, and it works because the HS norm is over the space variables, whereas the integral is over the time variables. So then again, we use the S of t as an isometry to get rid of this linear evolution operator, and we're left with the supremum of the integral of this norm of u mod u to the p minus 1 in HS. But from before we saw that this was bounded by some constant depending on n, s and p times the norm of u in HS times the norm of u in L infinity to the power of p minus 1 integrated over time. Now we can use the Sobolev embedding of HS into L infinity, because we chose s larger than n over 2, to bound this u in L infinity by u in HS up to some constant. So this gives us some new constant, CNSP1, let's say, times this integral of u in HS to the power of p. We can take the maximum of this norm and take it outside the integral, and then the length of the integral is t. So we can just bound this quite crudely by this constant times capital T, since the small t lies in the interval minus t, times the norm of u in C0t HSX, the power of p. So what have we shown here? We've shown that the norm of phi of u in C0t HSX is less than or equal to the norm of u0 plus this constant times t times the norm of u to the power of p. So this is now enough to show that phi is a contraction map when we choose a and t well. So in particular, we're going to choose a equal to twice the norm of u0, and then we can choose t equal to 1 over 2 times this constant times a to the p minus 1. Because then we'll see that whenever u is in this ball BAT, we have that the norm of phi of u in C0t HSX is less than or equal to, well, u0, but this is just a over 2, plus this constant times t, so that cancels with the constant down here, so we have 1 over 2a to the p minus 1, but then u to the p is bounded by a to the p since u lies in the ball, so this second term also, you can check, just gives us a over 2. So just a. So indeed, whenever u has norm less than or equal to a, phi of u has norm less than or equal to a, and so phi maps this ball BAT to itself. I'm just going to make a small remark that here we chose a equal to twice the norm and t equal to this, but actually we could have chosen a to be anything larger than or equal to this, and t then to be sufficiently small depending on a, and we would still have got the same result, that phi was a self-map on the ball. So we can now go on to showing that phi is a contraction on this ball BAT. So we want to show this inequality above, that whenever u and v lie in the ball, the difference between phi of u and phi of v in C0t HSX is bounded by half the difference between u and v in the same space. So the argument is pretty much the same as what we just did to show that phi maps the ball to itself. So we start by writing the difference between phi of u and phi of v as the difference now of just the Duhamel terms, because the free evolution parts cancel out because the initial data is the same. And as before, we use Minkowski's inequality to move the HS norm inside the time integral. So we have the integral from 0 to t of the norm s of t minus tau u mod u to the p minus 1 minus v mod v to the p minus 1 value at tau in hs d tau. So as we said before, this s of t acts in isometry, so has no effect on the norm. So we just have to evaluate this difference in hs. So again, we're going to use that p is an odd integer to write this as the difference of two polynomial terms. So we write u mod u to the p minus 1 minus v mod v to the p minus 1 as u times u bar to the q, again for q equal to half p minus 1, minus v times v bar to the q, which is u to the q plus 1 u bar to the q minus v to the q plus 1 v bar to the q. So this is the difference of two polynomials. We have u to the q plus 1 u bar to the q minus v bar to the power of q plus v bar to the power of q times u to the q plus 1 minus v to the q plus 1. Lastly, we factorize these differences. So we have u to the q plus 1 times u bar q minus 1 plus v bar u bar to the q minus 2, and so on up to v bar to the q minus 1 times u bar minus v bar. And we have something similar for the second term. So to estimate this in HS, we use this Leibniz type rule from before to put all of these terms on the right hand side into either HS or L infinity. So we're going to have a product of terms, well, a sum of products of terms with u's and v's and u minus v's in HS and L infinity. But we can directly use the Sobolev embedding of HS into L infinity to replace all the L infinity norms with HS norms. And then we'll get that this is bounded by some constant times the norm of u in HS to the q plus 1, just putting these all into HS, times the norm of u to the q minus 1, and so on, with that whole bracket, times the norm of u minus v in HS, and similar for the other term. And then you can just check that you can bound this by the norm of u plus the norm of v to the power of p minus 1 times the norm of u minus v in HS. So putting this into the bound above that we had for phi of u minus phi of v, we get that phi of u minus phi of v in C0 to HSX is bounded by the sup over the interval minus t of this constant CNSP times the integral from 0 to t of this at time tau d tau. We have u and v in the ball, so then the HS norms of u and v are both at most a, so we can directly bound those by a, or to a, and then we have the norm u of tau minus v of tau in HS. Again, we can take out the L infinity in time of this norm from the integral, bound the length of the integral by capital T to get CNSP times 2a to the p minus 1 t times the norm of u minus v in C0 T H S X. That's what I'm trying to say. So finally, to show this is a contraction, we need this term here to be less than or equal to half. So we choose T less than or equal to 1 over 2 CNSP times 2 to the p minus 1 a to the p minus 1. So let's call this 1 over CNSP 2 a to the p minus 1. And with this choice of t, we get that phi is indeed a contraction on the ball BAT. So now we're pretty much done. So comparing this condition we just got on t with the conditions we got before for phi to map the ball to itself, we see that if we choose a greater than or equal to twice the norm of u0 in HS, and t less than or equal to the minimum of these two constants we found, so the minimum of 2 times the CNSP1 that we had before, inverse, and this CNSP2 inverse, times a to the minus p minus 1, then phi is really a contraction map on the ball BAT. So this means it has a fixed point, and this fixed point, say u, will solve the nonlinear Schrodinger equation, at least strongly, on the interval minus t. So it's a local solution to the nonlinear Schrodinger equation. Okay, so just to sum up, let's put what we've proved into a theorem, just so that we're clear on exactly what we did just prove. So let p be an odd integer, s larger than n over 2. Then for any u0 in HS with norm at most m, there exists a solution u on some time interval minus t, which is continuous into HS, to the nonlinear Schrodinger equation, of course, with initial data u at time 0 given by u0. And this holds for any t up to some time tm, where tm is given by some constant CNSP times m to the minus p minus 1. Moreover, we have a very sort of weak, at the moment, uniqueness for this solution. We have that u is unique in the ball B2mt, which is the set of functions, as we now know, which are continuous from minus t into HS and have norm in that space at most 2m. So this just follows directly from what we just showed by taking a equal to 2m, which clearly is greater than 2 times the norm of u0, and tm is this that we found above. So here CNSP is just the minimum of those two constants multiplied by maybe 2 to the minus p minus 1. I'm just going to remark that we can actually do slightly better than this. So we did this for initial data at time 0, but by time translation invariance of the problem, you can easily do this at any time, initial time t0. So you can replace 0 here by t0, and you'll construct a local solution on the interval t0 minus t, t0 plus t, and obviously you also need to put in then t0s down here. And you'll have the same condition on tm, and yeah, everything just works exactly the same, shifted to time t0. So that's the local existence, we've proved it. Just before we move on, I just want to say maybe you want to think about this small thing, which is just something I find kind of satisfying, which is just to check when you take u0 equals 0, this theorem gives you what you expect. I'm not going to say what you expect because maybe if you don't expect anything, it's good to think about what you should expect. So that's just a little thing to think about. So now I'm going to say a quick word about the continuous dependence of the data solution map. So the map which sends the data u0 in HS to the solution u on some interval. Actually, we can get better than this just being continuous. We're going to show that this is locally Lipschitz continuous. So this is from the space HS into C0T HS X. So having just said we're going to prove this, I'm actually not going to prove this. I'm going to leave it to you as an exercise, and it's an exercise that you should do if you haven't already. And the reason is because it's just really similar to what we did to show that phi was a contraction map. But I'm going to clearly state the result, because actually just figuring out the result is kind of half the difficulty. And the reason for this is because you need to carefully choose the t in this space to make sure that all your solutions in whatever neighborhood you're showing continuity on are defined on this interval minus tt, because we know that the interval on which a solution is defined depends on the norm of the data in HS. So here's the theorem we have. So again, we let s greater than n over 2, p an odd integer, and I'm going to state this at any time t0 for the initial data. So we let m be greater than 0, and we look at data u0, v0 in HS with norms u0 and v0 at most m. So then if we denote by u and v the corresponding solutions to the equation that we just constructed in the previous theorem, and which are both defined on the interval im, which is t0 minus t of m, t0 plus t of m. Then we have that the norm of u minus v in C0 from IM to HS, so the space in which our solutions lie, is in fact less than or equal to twice the norm of the difference between the initial data in HS. So here this Tm is just exactly the Tm that we gave above in the previous theorem for existence. So yeah, I hope this all made sense. And just to finish off, I'm going to leave you with a small question regarding the nonlinearity. Now, this is a very open-ended question, so it's up to you whether you want to think about it for 0 minutes, 10 minutes, or the rest of your life. But the question is this: what exactly in the structure of the nonlinearity did we really need for the argument we just did? Could we have got away with less assumptions, or could we adapt our argument to work for slightly different nonlinearities? So some examples you might consider are these nonlinearities below, so some other polynomial nonlinearity, some nonlinearity which has the same kind of bounds that ours had, but not the exact same algebraic structure, or this one which is sometimes called a Hartree nonlinearity, with this convolution term. So here w is some function in L1, and we do the convolution of w with modulus of u to the p minus 1 before multiplying it by u. So the nonlinearity we looked at is kind of the case when w is a delta function. So maybe you won't be able to make the argument work for all these different types of nonlinearity, But then if you can't, maybe you could ask what kind of ingredients you would need to make some progress with the problem. Or maybe you can make it work for some specific values of parameters. The question is kind of yours to interpret. So yeah, that's all for now. I hope that you learned something, and see you again next time to talk about the uniqueness of solutions.